this stuff all the time. So while I'm paid to be an open source evangelist, scaling out applications is something that I think about a lot. And I think about it at various times. And I have this guy here, who's my son, Leonard. And what's interesting is when he was 1.5 years old, he was already driving Netflix on his own. And we could talk about users who get upset when they can't play a video or they can't order an item, right? But there's nothing like a 2-year-old who can't watch his damn cartoons because some database issue or some architectural issue in the cloud. And this didn't happen very often on Netflix. But it does happen occasionally. He gets really mad and equipment gets broken. So I care deeply about this for reasons other than just my professional life. And the reality is this guy growing up from his very first memories that he's going to have as an adult, being able to use these online applications with low latency, he expects it to always work 24/7. Many of us in the room, we remember the old rotary phones, or before we had a phone in our pocket and had the entirety of mankind's knowledge at our fingertips. But this guy and the generations growing up today, they aren't going to put up with any of the failures that we've seen. So our application architectures have advanced a lot over the years. People expect things to just frickin' work, right? Nobody wants to dink around and click through and go through extra screens and find errors and see 404s and understand what a 404 means and go back and try again. This isn't going to cut it, right? We all know this. There's online applications. This is a screenshot from Final Fantasy XIV, which is a massively multiplayer online game. These things are doing millions of transactions a second for things like people trading virtual items. And these people get really upset when things go wrong. And the way that these applications are built, I spent a couple of years at SOE, is different from the way that we build web applications at the time. And even today, we still build web applications very often the way we did 10, 15 years ago. And that needs to change. So the problem I'm looking at is when everything's working great, we have these funneled architectures. It's all good, but you need to design for max capacity, right? If we designed the roads around here in the Bay Area for the capacity 2 years ago, but wait, that is what happened, and look what we're dealing with today, right? Now we've got this capacity problem where we have all these people that want to drive to their startups from Gilroy all the way up to San Francisco, but the roads don't have the capacity to do it. And it's not a very great analogy, but it is kind of what we're looking at if we don't change the way we're building and designing applications. So a little bit about the evolution of application architecture. Just going to step through a few of these real quick. We have the classic client server. This is long dead. It still happens occasionally. There's still some legacy stuff out there that does it. Maybe some people remember when there were just terminals that connected to the mainframe or the database. And it was a direct connection from the fact client, either on a workstation or a terminal, to the database software. And that worked fine throughout the 80s and part of the 90s, but eventually we moved on because it didn't scale. We moved to the 3-tier architecture. Right? The red dots are clients up at the top. The blue dots are the application server, and then we have this big cylinder at the bottom, which is just any old database, right? It could be Oracle, MySQL, I don't care. It's all pretty much the same. It's a funnel-shaped architecture. At the end of the day, you lose capacity as that funnel grows, and then there's the funnel peak or bottleneck or whatever you like to call it. So Ruby on Rails is a great example of a funneled architecture. There's a database at the bottom of the whole thing. Nearly every web application in existence still targets this architecture first. And I don't think that's necessary anymore. And as we have things like Cassandra out there today, it makes even less sense because now your database can outscale your application. So we keep going with this, right? We can have master-slave replication at the database level. MySQL is great at this. Postgres can do it. Oracle has a couple options around it. Rack essentially looks like this because when you're running Rack, you still have the cylinder down the bottom. It's just one level lower. Here are your Rack nodes, and here's a big EMC array, right? Your symmetrics, or your HP XP 12,000 or whatever their modern array is. And you still have that funnel there, right? And you can add cache and stuff, but really what you're doing is you're papering over a problem. It's that your application architecture isn't built to be able to handle the throughput of all of your clients all the way through the stack, right? And the deeper you scale your stack, the easier things are at when you have load spikes. Now all of a sudden, whatever tier is being overloaded, you can scale out horizontally. Your database can scale out, your app tier can scale out, and your clients can keep just adding on clients. You don't hit that limit where you have clients coming on, and then you run out of capacity, and then you stop getting clients, not only because they can't log into your service, but because they don't want to deal with the bullshit of having a broken service. So this is kind of how I like to see things today, right? I think a new network diagram anyway is in order. And you know, we have the Cassandra rig in the middle, then we have our applications here, then we have lots and lots and lots of clients, right? And this keeps scaling. I built this and deployed these applications when I was at Uyala. We have lots of our customers that are building this way now, where they'll build a Cassandra cluster, they'll have a Yarn tier or a Mesos tier or a huge Docker infrastructure for deploying or horizontally scaling their app architecture. And that's easier because they don't have to worry as much about their database, which is by definition harder to move around. It has weight, it has data, right? And now we can scale further on every single tier because now all the tiers can scale horizontally. And then things go really well, right? And then your client load doubles and triples again, but we can keep scaling the whole infrastructure all the way down. We don't have to keep buying bigger boxes and going back to HP for another Superdome or whatever it is that we're using at the core. They come to the cost because now we've moved, what we've given up is the database isn't handling every single transaction around our data for us anymore. It used to be that you would do insert into, update table, which you can still do the same operations, but you got to think about consistency. A lot of you were here for Christos's talk about eventual consistency. He's probably talked, I didn't get to come in, but you know, I've known Christos for a while, and you have to start thinking about, do I actually need consistency here? A lot of times the answer is no. And then for when you do, we'll come to that, we can still do it with Cassandra. And it scales in a different way. But mostly what this talk is about is how do you think about these problems in such a way that you can arrive at the right architectures.
That looks like a jellyfish. Yeah. You could call that one a jellyfish.
Excuse me. So what I'm really here to talk about isn't network diagrams and funky architectures. It's how do we think about applications beyond where the read, modify, write cycle happens. Rather than stinking all of the read, modify, write down into the database tier, which is easy and convenient, it needs to be throughout the tier, right? We're looking at this one somewhere. We can do them here. We have lightweight transactions in Cassandra 2.0. So you can do fully consistent transactions at the database tier. But that has a scalability limit because these are more expensive nodes, right? And they have more gravity to them. They have more data. Moving that data around is expensive. It's really dry. So we need to move some of that logic out to our application tier. And even sometimes you'll see this happening out of the client tier, right? If you have a mobile application, it's gathering a whole bunch of data. It might actually do some of the mutations directly in the client. Security problems aside, people still do it. And there are still cases where it makes sense. Does this certainly make sense so far? So, what we want to talk about in terms of this is practical safety around how do we build data models to support these architectures. Eventual consistency, which you've already heard a lot about, so I won't overdo it. Different kinds of data models. So I'm going to talk a little bit about overwriting. So Cassandra has the ability of, because of the way upstarts work, rather than doing mutation necessarily, you can do a lot of things where you overwrite the same cell over and over and over. And it has some side effects, but it is evaluated to avoid a lot of problems. Key value, journal or time series style data, collection types, content addressable storage, which is kind of more esoteric, but it's a useful example to know about. And then finally, I'll talk about lightweight transactions for when you need And so, one of the things that changes when you move to an eventually consistent model is that you'll hear a lot of people talking about how you need to have a mathematical proof of cap theorem, or you need to prove that your system can do X, Y, Z. But this is the quote that I always think of when people tell me this, right? Is we've all built applications without knowing jack about all these mathematical proofs for these things, and they all work just fine. The reason why is well, we're modeling it sometimes in our heads without actually knowing the math, but also there's this problem of theory, the disconnect between theory and practice. So some of these things are not good ideas, but they're interesting to know about because they'll help you arrive at. So, you know, some of this comes down to safety. When you take all the safety off, right, you forget testing, and you just slap out some code and throw it out there. You can do it really fast. You can do some wicked cool stuff, right? But, you know, you might set your pants on fire. I hear that's unpleasant. I've experienced it myself. You can do a little better, right? We can build a dangerous system, and then that looks dangerous on the surface. And this here is my favorite, is the rocket on the back of the car. But you know, this thing has a roll cage in it. There's a 5-point harness installed in the driver's seat, and the driver's wearing a fire retardant suit and a helmet and gloves. There's a lot of different ways to mitigate failure, besides just building everything to, well, the Japanese standard, right? So this is the Shinkansen, just cruises at 320 kilometers an hour. It's almost 200 miles an hour that train moves. And the amount that they spend on making these safe, and the amount of effort it takes to keep the rails smooth and to make sure that all the curves are done right is incredible. It's an incredible amount of work. We can't do that in our daily jobs most of the time. Most of the time, we don't have the time, we don't have the resources, so we kind of got to go back to that middle ground, right? So when I'm talking about these different architectures, that's what I want you to be thinking about is some of these are kind of crazy. Content addressable storage isn't that useful in practice, although almost all of you use it every day because that's how Git works. But when you're thinking about this and you're moving out and you're doing these mutations in your applications here, not to get too fed up or too tied up in the theory of how to do it right, because you're not going to get the job done. So, read, modify, write. Did everybody understand? Maybe take a poll. How many people know what I mean when I say read, modify, write cycle? Awesome. Okay. Good. This is good material. So I want to do a mutation on a record. So what happens is I want to go and say I get promoted, right? Patrick decides he wants to go back out in the field, and now there's an open spot for chief evangelist, and I have seniority, so they promote me. It's not going to happen. And I can't, my hair doesn't stand up like that, so I can't have the job anyway. So we need to update my rank in the company from 3 to 4, and we need to update the last promotion date because, of course, we would track all promotions because you can't promote people too fast. This is the corporate world, right? So I read, modify, write. What I mean is in order to mutate that record, we have to read the old record off of storage, pull it in the main memory, and MySQL is doing this, Oracle's doing this, everybody has to do this to mutate records. You pull the data structure out of storage, it could be on disk, it could be in memory, it doesn't really matter, right? You make the changes to that data structure, and then you write it back to disk. So you read, you modify, you write. If it's Redis, it's all in memory. If it's Oracle, it's really complicated. If it's Cassandra, it's the same thing, right? We read it off of disk, you actually read it in your application most of the time, you do the mutation, you write it down. Now everybody knows what read, modify, write is, right? Awesome. So this is the thing I want you to be thinking about when you're building your applications. If you think about it in terms of whenever you're doing updates or inserts and you want to make a change, where is this read, modify, write happening in my infrastructure? What server layer is it going to happen at? And that big ring, it's probably not happening on your client devices because there's a security nightmare there. There's no way to tell devices you don't control are going to do with the data. So it's probably going to happen at your application tier because we don't have stored procedures or anything like that. That's long dead architecture, I hope. But when we go into the distributed systems world, it introduces a new problem, right? On a single node, we have CPU instructions that will take care of locking for us, for example. Or we have atomic compare and swap. But when you go to a distributed system, you have to have a consistent view of what the data is at any given point in time. And so when I do this mutation and I talk to one node in the database, and that node fails during the transaction before it's replicated off that node, we got a problem. So we have tools to deal with that, right, Cassandra? Generally, this isn't a problem. Because what happens is before this write gets returned back to the client, it's going to have replicated. So that's one thing to remember, is your client will throw an error if there's a failure in the middle of the transaction, and you will get an exception back. So it's safe to do these out inside your applications here, is kind of what I'm getting at. Whereas it used to be, your DBA would tell you, oh, use stored procedures for all of your business logic, because then it's in the database and all the consistency is managed there. Well, that doesn't scale because now all that code is running on one node, or a small group of nodes, and you can't scale it as easily. Because now you have to scale your database, which means you have to scale your data or your storage systems and expensive, qualified hardware solutions. So, quick explanation of what I mean by ReadModifyWrite, and then on to data models. So, overwriting is an interesting use case. I'm going to just cover a quick one that I've done before. I was working on a monitoring system, and one of its key requirements is it needed to be able to support instances in EC2 that came and went hundreds a day, right? Kind of similar to Netflix's, not quite as aggressive, but we would spin up, a new cluster of 16 machines, and they would enter into the monitoring system and start dumping data in, and then 2 days later, they might be gone, replaced by other nodes. And they're cycling really fast. This didn't used to happen. 10 years ago, you built 25 boxes to run the application tier, and you left them sit there, and that was it. If you added more, you'd add like 5 more, and you'd configure them and put stuff on them, and it was no big deal. The monitoring system didn't have to care how fast nodes were coming in and going. So host names used to be how we addressed all those systems in that day, but today it doesn't make any damn sense at all because these nodes are changing so much that host names have no meaning at all. So we needed to apply some kind of ID or some surrogate key to the systems that allowed us to address them across all these iterations. But now we have a problem because humans want to talk to host names, and all of our tools want to talk to host names and IP addresses. So we needed an index that we could use that tied the GUID back to host name. So this is common in a lot of applications that you're probably working on, especially with Cassandra. So we didn't want to have to write like some daemon that basically would go and do the mutations, right? So one option would be to have a service, and a node could register with that service and go and say, hey, I'm GUID, blah, 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 and here is all my data, and please go and update my record. And it would go and read it from the database, update the record, and write it back. But why would we bother doing that first read? It doesn't matter, right? This is kind of one of the lessons of big data. Maybe we just write a new record every time. Well, after a while, that would get kind of waste a lot of space. So what we did is we created a time series schema where there's a daily bucket for these indexes. So on any given day, you can pull back that index and get all of the hosts for that. And it wasn't that big, it's like 25 megabytes or something. And instead of mutating records in there, we just, every hour, the node would send the same registration information every hour, all the same stuff, and it would just write it into the database. It never read it. Only the clients ever read it. So the nodes generating the data had no clue what was being held in the database or how. And the service that was actually updating the records never actually read those records either. It just wrote them. Everybody with me? Has anybody ever tried this before? Cool, cool. So you learned something, good. So what you would do is instead of, you would look up you take that host GUID, and the daily bucket's easy to compute, and you just go and you get your record, you serialize it, you write it into the database. Boom, done. Never read it on the server side. And then when a client wants to know that information, then you finally read it. But you don't have to care because if you overwrite it 100 times throughout the day, or 24 times, it just doesn't matter. This has one big downside. We've completely avoided read-modify-write cycles throughout our architecture for the write, and on the read side we don't have to worry about locking or anything. But what to watch out for is this is not good for a high throughput solution in a lot of ways, because what you'll end up with is a compaction problem in Cassandra, where what's happening is when you do a lot of overwrites, you can end up splitting that row. Your partitions will end up getting split over many SS tables, especially if you're on LCS. So you write the record, an hour later, the mem table's been flushed. I thought I had a screen for that. So the mem table gets flushed to disk, and then maybe another one does, the compaction required, another one. And then finally, when you want to do these reads, now you have to read all of those SS tables to find the most recent record. And then when compaction comes along, it has to take them all, merge them, and put it back down into a smaller SS table, which causes I/O. So if you're doing a lot of overwrites, it can cause problems with compaction. But for simple cases like this, it's not even worth thinking about. Just do it. Another one is key value. So Cassandra is just finding key value. The core OSS developers on Cassandra hate it when I say this, because they don't want to be a key value store. And it's not a great key value store, it's just a good key value store. So I say use Cassandra for key value when you've already got Cassandra deployed, your application's already connected to it, and you have some key value data you want to manage. Throw them in a table in Cassandra, and be done. You don't have to worry about synchronizing memcached, replications taken care of. It's all basically happening in memory. And there's one little trick you can do by, if it's mostly ephemeral data, you can turn off durability on the schema, and that saves you a little bit of I/O on the commit line. So in general, this is more of a utility thing. You got a bunch of brand new data you want to store. This is a nice little pattern. What this does, though, is it forces the read, modify, write up into your application, just like memcached does, right? There's no same way to do that in the database here. Well, you could use LWT, but that would be just for consistency. And then this is kind of our bread and butter data model. How many people went to Patrick's data modeling session? So it's not totally good. Cool. So this is kind of the simplest time series data model I can come up with. We have the time bucket, which looks kind of like this second one down here. So you take the date and you truncate it down to some arbitrary time. It's not arbitrary, actually. It's some easily calculated aligned time. So you align on 5 minutes, 1 hour, 1 day. Nothing bigger than a day really makes sense, right? How many people can define a week in programmatic terms and teach a computer what a week is?
It's not easy.
It's not easy. It's a lot of work. And it's incredibly computationally expensive. And the worst part is it's not a technical problem, it's a political problem. Right? Time is defined by politics. At least wall clock time is. Leap seconds are a political body that says when leap seconds happen. Daylight savings time, I mean, if I ever got to meet Benjamin Franklin, I would like to smack him for that. So we have our time bucket. So like I said, 1 hour is great, 1 day, depending on if it's low, a relatively small amount of data, a 1 day bucket makes sense. 1 minute sometimes makes sense, and even occasionally 1 second if it's really, really high throughput, right? Not very often, usually 1 minute. So most of the stuff we did in this monitoring system was 5 minutes and 24 hours. The next one is the actual time, right? So the time bucket ends up being your partition key, and then the time is how you index. That's basically, if you know the old thread model, that would be your column key, right? And then whatever you want in the value. I said blob here, you can throw a bunch of JSON in there. We don't really like it when we store JSON in there, but it works. But you could have a whole extended table there with a whole bunch of attributes, right? It doesn't matter. This is the simplest thing that could work. And then inserting your data looks like this. And that's a simple time series data model. Cassandra is really, really good at time series. And the thing is you can model a lot of things as time series that you don't realize as time series. Right? Like I was just talking about host information. You have 10,000 servers in your network, and if you decide to, instead of having just a table of hosts with 10,000 entries in it, if you had a daily table or bucket of host information, now all of a sudden you have this nice, convenient snapshot of your network every day for free. And what we found was that was useful over time. People would come and say, hey, how many hosts did we go through last month? And I go, well, I'll just flip through the host table and go back, and I can actually go and grab the GUIDs, and I can track back and get the instance types and all that stuff from the monitoring system. because I have the last 6 months of daily snapshots of what our inventory is. So it's interesting to think about that, especially when you're working with time series. A lot of things will fit into a time series schema that don't necessarily up front look like time series data. And you got to think about it in terms of snapshots, right? If you use ZFS snapshots, occasionally you get that same effect for free. Because you can go roll back and say, well, what did that look like 6 months ago? Whoops. So this is kind of useful for whiteboards. I like to throw this in, and this is another one I get in trouble with the core people when I do it. Especially this one here. We'll start here. So this is kind of another way to kind of draw what a time series schema looks like. Sometimes it's hard to imagine, to model in your head what your data actually looks like. So I like to give ways to think about this or to visualize it. So we have the same data, right? There's our bucket, timestamp, there's some data, maybe it's JSON or something. And what happens is when it gets stored, this is actually kind of how it looks when it's actually stored on disk. Cassandra will store, especially time series data where time is a key, will store that data in sorted order on disk. It actually does it in memory too. But this is really useful because you can do things like single seek access to a window of time, right? And you can do range queries across this. And this kind of makes it easier to see that. So when you do a range query, you want to go from point A to point B. Maybe there are a bunch of other actors in the middle there. But this also ends up being a single seek on disk when you're going to disk. And you go and say, give me this slice from inside this partition, because it's all stored in sorted order. Cassandra knows exactly where that data is and can instruct the operating system to go and get exactly those blocks of data that it needs, which is very efficient. The second one is I use this for whiteboarding, Cassandra data models. This is from the bad old days of Thrift. But it's still useful when you're talking about the storage side of things in Cassandra and performance, is this kind of nested map. So when I'm drawing a whiteboard and I'm trying to do a model with somebody, I'll actually do that, open map, here's my partition key, and if I'm doing a compound partition key, I'll just put some kind of separator like pipes or something, and then use the fat arrow and then more maps. So I'm not going to talk about that a lot, but just kind of keep that in mind when you're thinking about data models and whiteboarding them. This is a little more useful sometimes than ER style diagrams. Content addressable storage. So this one's really interesting. I think there's going to be more to content addressable storage in the future, but the big one that everybody uses every day pretty much is Git. So that's how Git achieves its speed, and that's why you see these funky hash values for version IDs instead of integers like you're used to from, say, Subversion or other CVS. So all they do is, content addressable storage says that the address of my content is determined by the content. So Git uses SHA-1 checksums, which are cryptographically mostly almost secure. SHA-1's been broken a couple times. It could be MD5, or now Cassandra uses like the Murmur 3, which is actually a good algorithm for this kind of thing. So you just take your payload, which I'll step through the code right here. So this is just a little bit of Ruby. This red here is red, so I don't forget to tell you that this is a terrible thing to do. This will not work in production because it has no guaranteed ordering, so you can get you'll get different addresses each time. But it's just the shortest way to show a serialization that fit on a slide. So we're going to use SHA-1. We connect with CQL. We say we have a key space defined as CAS. And then we create a data structure in Ruby. So this has nothing to do with Cassandra yet. We take a checksum of that data after it's serialized. So this could be JSON encode or protocol buffers or whatever. Generally, Cassandra, you're not going to do that very often. If you're storing logs, that's how you would do it. And then we just take and we get the hex string for that checksum, right? And then that becomes our content ID. So if we want to get this same content back, we're going to query on content ID equal this checksum, right? It could be some hex string that's 36 characters long, whatever it is. Everybody with me? Any questions? Cool. So for inserting content, we're going to do insert into CAS value, with this is our content ID. Now, this has some downsides, right? You have to maintain a lot of indexes to be able to actually get to your data afterwards because it's essentially random IDs. They're hard to predict without actually having the data. But the way Git does it is it just generates these lists of SHAs. If you look inside the .git directory, you'll see these, like master or your current branch. There's just a little text file in .git / I think capital head, and it'll just be the SHA in a file. And all Git does when it wants to know that is it just reads that file, the whole thing, and then it's got it. And your file tree is actually just a big long list of these SHAs, and the history as well. So those are a few models that don't actually require ReadModifyWrite to get work done. But at the end of the day, we've been programming with SQL databases for some cases. I've been doing it for 15 years. Some of you have probably been doing it for 20 plus. I'm not going to point at anybody. And some people may have for a couple of years, but if you're in university and you're learning about databases, you probably did some kind of SQL database. So you're used to being able to do this in the database, and sometimes it's just, you just want to get the job done and you want to use it. So that's why we have lightweight transactions now in Cassandra. But lightweight transactions aren't the only way. So another way is with our collection types. The maps and sets in Cassandra are CRDT. They're safe to modify without locking. So you can do inserts and updates into sets and maps without any locking, and they're fully consistent. A lot of people don't realize that. So this example, that's my dog. He's a puppy. He's really stupid. And so I was talking to my Japanese teacher, and I said, yeah, there's a phrase I use around my house a lot. And I say, baka-yo, which is basically saying stupid dog. Or, baka-man, you see how stupid my dog is? And it turns out that doesn't translate to Japanese at all. Because she just looked at me funny and she said, stupid dog? Yeah, he's, stupid dog. Like you just say, you meet a new dog, you go, hi, who's a stupid dog? Apparently that's not a thing outside of America or at least Western world. So anyway, I decided to use this example because this is Tobey, me, Inu, Baka, Ne. So, anyway, we're almost done. So, maps and sets, this is kind of how you use it. What are we using there? We're using sets. I have a blog software. I want to have a set of authors and tags. I don't need to be able to have multiple entries with the same key. So I can have the maps and sets. I can add authors, remove authors, all these things. It's fully consistent. I don't have to think about it. Same kind of thing for maps. Maps are basically like maps that you expect in Java or Python dictionaries or whatever. They behave in a very similar way. Again, they're cheap and easy to modify. You don't have to think a lot about consistency there. Then there's lightweight transactions. Has everybody heard about lightweight transactions? You know what they are? Great. Real quick. Looks like I'm running out of time. What it is Cassandra has now an ability to use Paxos in the back end, so that when you do a transaction, when you're making a change to the database, you can set these little clauses, this if username equal awareness or if not exists here, and it will actually do multiple round Paxos to make sure that all the nodes in the transaction agree on the value before it returns the commit back to your client. And if any one of those nodes is out of sync, it will return an error to you. So you always know that the data that you committed now will go to disk and it'll be exactly what you expected. And this is guaranteed by the database now again. The downside, it's a lot slower than all the other stuff I've talked about. Because now it has to talk to all those nodes in play. So if you're on R equal 3, all 3 of those nodes have to agree and report back to the coordinator that they agree, which requires multiple round trips on the network. So realize this is for like the 1-2% of your application where this is absolutely necessary. You should be using every other possible technique when you don't absolutely need this. We can talk more about lightweight transactions outside. We'll take a lot of time. But in conclusion, we're scaling further, faster than ever. your application architecture, the three-tier architecture isn't going to get us there. And you need to think more about every level of your tier scaling out wide. Because Moore's law has failed us pretty much at this point. I mean, it might pick up again, but we can only shrink the process so far. And barring another big jump in CPU technology, we're not going to get bigger boxes again for a really long time. So think about where those mutations are happening and strategically place them. And it's more important than where you place than a lot of the other factors that maybe you think about before, right? What library am I going to use? Blah, blah, blah. What kind of servers? Think about first, where is the mutation happening? And then let that drive a lot of your other decisions. How many application servers? How many database servers? What kind of network am I sitting on? How many availability zones am I going to be in? Those are the things that you can drive thinking about where is the mutation going to happen. And thank you. Any questions if we have time? Do we have time? I think we have like 3 minutes.
Why do the marketing guys call it lightweight if it's like 2 extra reads and it's really heavyweight?
It is, and I think it's because the syntax is very lightweight.
Ah, so it's very easy to code even though it...
I mean, we call it a lot of different ththings internally. LWT is kind of what we call them, and they are a lot lighter in terms of Cassandra, they're very heavy, but in terms of distributed systems in general, they're actually fairly light, right? Doing distributed transactions in general is usually very, very expensive, and we've gotten it as cheap as we can. It'll probably get a little faster in the future. Yeah.
So it's as light as possible.
It's as light as we can do. Yes. Cool. Well, thank you very much.